is about a specific coarse-grained model of DNA. So I will, I think I got it. Okay. So it's called oxDNA, Ox like Oxford. This is where they developed it first. Very smart move to put like the name into the name of the model, the name of the town. And so that has evolved. It's kind of like a very popular model. And it's seen increased use, and I'm going to tell you a little bit about that, but mainly from what is the software suite and how can you run this from that point of view. So, you know, with these hands-on tutorials, there's always two options. Either you can do something scientifically really fancy that you work on, and then you need to provide all the data and you run just a few scripts. Or you do something that is a bit more low-key scientifically, but then you run the stuff yourself during the workshop and actually use the software. So I opted for that second option. And so here's a short. So yeah, my name is Oliver, German accent, English name. Blame my parents. So I work at the University of Strathclyde, which is in Glasgow. You always need to say that because Strathclyde is the name of an ancient kingdom, medieval. So where's Strathclyde? It's also half of the population of the world can't pronounce it. So maybe not the smartest move, but anyway. So I'm now based in Glasgow, and here's a short, oh, that doesn't work. Here we go. Here's a short outline. So first, I will just introduce this model and say something in general about coarse graining. So what is the idea behind it? There's two different flavors. Then introduce the software. What is it? What packages are there? There's 4 bits that we're going to use. And also briefly say how you can get it and compile it. And then we can maybe have a break. So that should take, I would think, an hour max. Then we can have a break, sort out like the job submission scripts, put them into the repository. And then we can run stuff on Arc, or you can run stuff at home if you manage to compile. We describe in the second part. So this whole tutorial is, I'm doing this for the very first time, so apologies if it's if there are typos or whatever, so we need to see how it goes, in other words. It's available here for my GitHub profile, and there are 2 directories. One is called slides. These are the slides, the later code of the slides, and then there's one exercise, and we're going to work in this exercise directory. So you can clone this locally, or then as well, but we should do it later on the Arc. You can clone it there. That is most convenient then. And then we need as well just a web browser. Yeah, anything will do. Chrome, I think, is optimized, but it works as well with Safari and Firefox. So tried that. So starting with the model itself, like DNA, maybe a few facts. It's always good to remind yourself how amazing this molecule really is. So the double-stranded DNA molecule is about 2 nanometers wide, but if you take all the DNA in just one of your cells, it's 2 meters long, and put it just together, it's 2 meters long, yeah, in one cell. And what's also amazing is if you can take the array of all of your cells in just one human being, it is about 100 astronomical units. So the distance to Pluto, not a planet anymore, is 40 astronomical units. The astronomical unit is the distance between the Sun and the Earth. Yeah. So the DNA in all of your cells, 100 astronomical units, or what's probably better, about 0.6 light days. It blows your mind a little bit. I think it's beyond comprehension. And someone told me a long time ago, when they started, well, first of all, they found DNA, but they didn't know it. Oh, sorry, before they found DNA, because they looked at cells and they found something that was just everywhere, and they called it the stupid molecule. They had no idea what it was, but this kind of like explains why they saw it everywhere. Yeah, the stupid molecule. So the stupid molecule consists of base pairs. So you've got about 3 billion in one of your cells. Base pairs, that's the human genome, and the structure is roughly is shown here at the bottom. So you've got like the double strand, and then the first stage of organization is around these histone octamers. So it's a protein complex, roughly spherical. So the double strand wraps around it about 1 2/3 of the time. Yeah, and that is already 200 base pairs. So these loops are the histone octamers. Then these histone octamers organize, they pack together. So it's also called beads on the string for obvious reasons. They organize together into a solenoid or a 30 nanometer fiber. This is what it's called. This is another level of organization that's shown here. And then it loops. And then eventually it goes into chromosomes and all this. Yeah. But a loop around, well, it's not 200 base pairs, it's exactly 147. I put the number here. It's one loop around the nucleus. They're also called nucleosome core particles, histone octamers. And then a loop like this here is already in the range of like several 10,000s of base pairs. When you describe every single atom in DNA, what you can do normally is, I think Sarah might agree or disagree, but I think 3,000 base pairs, does it sound like something that is...
That would be quite big.
Quite big, exactly. I didn't want to be, I wanted to be generous.
Yeah,
so Sarah says 500,
Thanks,
but I know it's already, I mean, I don't think we're talking about 3,000 at all. So the actual figure is 500. You can do 500 base pairs. So put this on that scale of these base pairs, these loops here. And another problem is, of course, it's not just the number of base pairs or physical length, it's also the time scale that you can do. You're talking about the microsecond time scale. So these are just intrinsic limitations that you have when you use atomistic models that have everything very, very finely resolved, which explains why you need something else if you want to study DNA on larger time and length scales. And this is why you do coarse-graining. So to coarse-graining, you're able to access milliseconds normally and mega base pairs, yeah, and even beyond. It's just it's always then a question of how much pain can you face as everything goes big and becomes super difficult to handle. Yeah. So oxDNA is one of those efforts, and I can cite maybe a reviewer from our proposal said, like, they claim that it's the leading model is a justified one. Yeah, and the reason is oxDNA has a few design features that really distinguish it from other coarse-grained models and have significant advantages, which is why the model has seen an increasing take-up. My collaborator Tom Aldrich at Imperius developed this originally, the first version in his PhD. That was 11 years ago, and since then there's over 200 publications that actually actively use the model for the work, and half of them about within the last 2 or 2.5 years. So you see, like, there's a kind of like growth, and the model is the key idea is that each nucleotide is just described as one rigid body with position and orientation. Other coarse-grained models use more than one body, like 3 beads for instance, per nucleotide. So they've got a slightly finer resolution that leads to other problems further down the line. So oxDNA has just one, and I'll just point this out. So this is often how it is visualized. But we're talking about just one rigid body. This is just for visualization purposes that you draw something like that. Yeah. Physically, what it is actually a rigid body, spherical, with a moment of inertia that is the same for all axes. Yeah? So you have on this rigid body, you have 3 interaction sites, and this is highlighted here a little bit. So you have one which is called the backbone interaction site. Then you have, which is roughly here. So the shape indicates a little bit where these interaction sites are. Then a stacking interaction site and a hydrogen bonding interaction site. There's going to be another slide, I think, after this, which explains this in a little bit more detail. And then, so these are kind of like fixed on a rigid body. And then you've got 7 interactions between these rigid bodies that with distances are taken with respect to like these interaction sites. So one bonded for the backbone connectivity, and then 6 pair interactions. And this is really the key difference. It is pair interactions, so they involve only 2 bodies and not more than 2. Other models use angular interactions as well, dihedral, which involves in multiple particles or nucleotides. So what oxDNA achieves here is, by this simplification, is you have 13 degrees of freedom, where in an atomistic simulation you would have over 200. So 13 degrees is 3 positions and translational momenta, then 3 angular momenta, and 1 unit quaternion. A quaternion is something that you often don't come across when you study maths or physics or whatever. Think of it as, I mean, you're familiar with complex numbers, and then you can, a complex number can define an orientation on a sheet of paper in 2 dimensions. Yeah. And the quaternion is the analog or extension of this concept or idea into 3 dimensions. That's what it is. So it's like complex numbers, and you've got similar rules, just more of them, and that allows you to describe with 4 degrees of freedom the orientation of a rigid body. Yeah. If you're familiar with like Euler frames or something, the minimum there would be 6 degrees, because you have vectors. You have 3 vectors, like a local reference frame. So you have 2 vectors that are orthogonal. It's like 6 degrees of freedom together, and then the third one you get for free because they were orthogonal to the other 2. Yeah, but you need 6. With quaternion, you need only 4. So this is in short like how this model is cleared up, and you see here this is often how a nucleotide is visualized. Then here in D you see a duplex formed, and these interactions are sketched out here on in this picture C here. Yeah. So this is what a nucleotide really looks like, and how you describe that. There's a version 1 of oxDNA, which is shown here on the left side of this picture, and then oxDNA 2, which features the major and minor groove, quite important. And this is achieved by, you see like this green sphere here. In fact, the rigid body that I talked about, think of it as just something that comprises these three sides. So you've got a backbone, a stacking, and a hydrogen bonding interaction site. Yeah, but the whole thing is on one body, and this is already a base pair. So you achieve this major minor groove feature by angling the backbone interaction site away from this base vector, which is just connecting the stacking and the hydrogen bonding side. So if you want, like the base vector is here, this horizontal direction, And then you've got the base normal, which I think points away from us into the paper, or like into the screen. And then you've got the orthogonal third vector, which I describe here as y. So if you have a center of mass of this rigid body where the backbone interaction site is, this is just 0.4 length units away from the center of mass in direction of the minus direction of the base vector. In oxDNA 2, you have that. So you've got this y component as well, which is this third vector, yeah, it's that leads to this angled configuration. The stacking interaction site is just 0.34 length units along the base vector direction, away from the center of mass, and the hydrogen bonding site is a little bit farther away, for 0.4 length units. So this is the basic layout of a nucleotide, and what you have then in your ND code or whatever it is the center of mass, and then you kind of need to work out where's this actually interaction site now. So you take distances, for example, the backbone interaction with respect to these backbone interaction sites on the nucleotides. This is how you do it. Yeah. So the whole thing, I will show this image here to highlight a little bit the complexity of this model. This whole approach is called the top-down approach in coarse graining. So top-down means you make a sophisticated, smart assumption of like what these interactions look like. So you put this in, and then you parameterize it in a way that you get the right physical behavior, mechanical behavior. Yeah. The other way to coarse grain is what's called bottom up, and bottom up is different in the way that you start really with your atomistic system, which has all these 200 degrees of freedom, and then you devise a sophisticated scheme how you can kick out degrees of freedom and reduce the number of degrees of freedom. Yeah. I've never worked with bottom-up approaches, but my gut feeling is that doesn't really work when it reaches a certain level of complexity. I don't know what your opinion is, Sarah.
Well, I was just thinking about this because atomistic force fields are bottom up, aren't
yes.
they? But it's quite, there's an intuitive assignment of partial charges to atoms, and so it sort of works. But FFEA is top down.
Top down.
Yeah. And the machine learning algorithms will help us do both.
Yes, yes.
I mean, this is one instance where machine learning, I can see it's really useful, because it doesn't matter if you don't understand it.
So we're going to develop a new version of this model over the next few years, and we also use a machine learning approach for parameterizing this. It's just, there's no other way you can do this. So the complexity is you wanted to have the right mechanical properties, but it also DNA denatures. So the base pairs come apart at a certain temperature or when you apply a strain. But then if for example, that's what we're going to do in one of the exercises, we just boil it 100 degrees. This is what I said in simulation, so it denatures. But then if you cool it down, it comes back together. Yeah, so it's fully reversible, which explains as well why it's really an interesting material for nanotechnological applications. But coming back to these relative distance vectors, so it's just don't get disturbed by the details here. If you just get the spirit of how it works, I think that would be more than enough. So you see, if you can define relative distance vectors between these interaction sites. So I call one back and then the other one stack and then base for obvious reasons. And then you've got also relative distance vectors that mix things up in a way. For example, it's the distance between the backbone interaction site on nucleotide I and the base interaction site on nucleotide J. So these are also possible. And with these relative distance vectors, you can define angles. And I don't know if this is clearly visible on your screens, but there's, for example, this θ1 angle, which appears here in this small image C, and that is simply the negative of the projection of these base vectors. So it tells you in a way how the base vectors are oriented with respect to each other, to nucleotides. Yeah, and for example, the θ2 is then here. Yeah, so that involves a relative distance vector between the base interaction sites and a base vector of one nucleotide. This is in principle how you use these relative distance vectors then to get also angular information of how these things are oriented with respect to each other. For simplicity, I mean, this is all this oxDNA 1 model where everything is collinear. That just makes it a little bit clear, a little bit at least. And so this is how you introduce spatial and orientational dependencies in functions and so on. Yeah. And then comes where you actually use these things. There are a few very elementary potentials that are used in oxDNA. Maybe starting with the phenol backbone, you want to have something that extends in a way, but not too much, which is why they picked the phenol potential. Phenol is finitely extensible, nonlinear, elastic. I think this is what it stands for. So you see there's a logarithm that appears here. So it simply means you extend further than, like, it's finite. Yeah, it's finite in other words. This is where the F comes from. Yeah. So this would be a phenol potential which appears solely in the backbone interaction to model the backbone connectivity. Then you've got a Morse potential that is used in stacking and hydrogen bonding. Harmonic potentials in cross-stacking and coaxial stacking. Then a Lennard-Jones potential for excluded volume, so that you don't get crossing of strands, so they repel each other. And then various quadratic terms in angular or form mostly, which describe these angular modulations, so how the potential forces change as the orientation of the nucleotide changes. And then smoothing terms just to get no spikes or discontinuities in forces, so that you have kind of like you tape it off to zero as you go towards the cutoff. Yeah. Then oxDNA 2 introduced an electrostatic dependent as well. For that, in the spirit of staying in the coarse-grained picture, they used a very popular but approximate description. This is dBi-Huckel. So it works well. The dBi-Huckel in general describes systems that are charge neutral. So you've got counter ions, but if you have an ion, then you've got like a cloud of counter ions that sort of screen the field of that one ion. Yeah. So the range of these interactions is not infinite as you have in a Coulomb field. I mean, the Coulomb field is infinite. This is, yeah, 1 over r, but I mean 1 over r never goes really to zero. But in the context of having a system that is in ionic solvent, these electrostatic interactions are screened. So it's very simple. It's also a pair action, and if your ionic strengths are not too high, then it offers really a reasonable description. So these are the basic potentials that somehow appear somewhere, and then it gets maybe a bit more confusing when you see you can, with these potentials, you can define these modulation factors F1 up to F6. So you see these potentials, for example, Morse potential appears in this F1 factor, but then it's only, the MOS is only active in a certain range, so there's then smoothing, and goes then to 0. F3 is certainly a modulation factor that occurs in the excluded volume interaction, yeah, because it contains the Lennard-Jones interaction. And this is kind of like, don't get caught up in the details. You have these basic elementary functions, and they are used in these modulation factors, and then the actual interaction of the oxDNA force field is like this. If you just look first at the bottom of the page, so you've got you can distinguish between nearest neighbors on the same strand, and then all other pairs. Yeah, nearest neighbors on the same strand, they interact through a backbone interaction. Then excluded volume and a stacking interaction. So the nucleotides stack. This is a very dominant interaction. oxDNA gets this also right. It is also energetically really dominant. And when it denatures, you actually need to do two things. People always think of like, well, it's the hydrogen bonds that you need to break, you also need to unstack. Yeah, it's a really significant contribution. And between other pairs, you have the electrostatic interaction, the hydrogen bonding, if they're complementary, and then stuff that is called cross-stacking and coaxial stacking. Yeah, I think this is, for example, a typo here, so I mentioned this twice. So I should get rid of that. And these potentials are then defined in this way here. The backbone interaction takes directly this feeder potential. It's probably the simplest. The others, they are somehow constructed out of these modulation factors that we just saw here on the previous slide. If you take the excluded volume interaction, you see it's this F3 modulation factor, and it's active between backbone sites of two nucleotides, but then also these cross terms between backbone and base interaction sites, or just between the base interaction sites. So it contains actually 4 terms. Yeah, unless you are on the same strand, then you probably don't want this one here, the back between the backbone interaction sites. Why? Well, the distance of in the backbone connectivity, well, that should be controlled not by the excluded volume, it should be controlled solely by the female backbone interaction. So you omit this term when you're on the same strand. This is why this prime here occurs. But in general, you have these 4 terms, and then stacking contains some other factors, hydrogen bonding. So you see it's quite involved, and this is in principle how these interactions are constructed, what they look like. The electrostatic is then again very simple. This is just directly by the Go interaction, and you look at the backbone distances. Yeah. So you see is 1 bonded and 6 pair interactions, and as I mentioned earlier, this is really the key advantage of oxDNA, because other coarse-grained models they use also angular potentials, which involve 3 atoms, or dihedral potentials, which involve 4. And the main problem is when DNA denatures, its structure changes profoundly. Yeah, the persistence length is this measure that tells you how quickly you lose orientational correlation. So how quickly this thing curves. Yeah, if you think of like a spaghetti, which is maybe not the best example, because I think the persistence length of the spaghetti is something like the distance from here to Pluto is like really crazy. So it doesn't give you a good feeling for it. But in DNA, it is about 50 nanometers, 150 base pairs. So the orientation correlation decays to a factor of 1 over E over 150 base pairs. The further you go away, the less correlated an orientation will be. And basically, if your first segment of your DNA chain points upwards, something that is 1,000 base pairs away won't give a damn what this thing, where this first one points to, yeah. But if it's only like a few base pairs away, then there is definitely a strong correlation, and this is what the persistence length describes. So there's 150 base pairs in double-stranded DNA, and it's only about, well, it's disputed, but say all of 5, roughly 4 or 5 base pairs in single-stranded DNA. So the double strands come apart, and it's like a factor 30 drop in this quantity. If you have only pair interactions, you can get this right, and oxDNA gets this right. But if you have interactions that involve 3, 4 more atoms, there's always a residual effect then of what you parameterized it on, despite undergoing this denaturing transition. So you've got what you normally want to describe is bDNA. I had this on one of the first slides, I think, but forgot to mention it. So it's the most common form of DNA. So you parameterize your coarse-grained model to describe bDNA, and then it denatures, but there's still something of that bDNA then in your single-stranded DNA. Yeah, this is where many other efforts of coarse-grained DNA models, have disadvantages. I don't say they failed, but oxDNA is really superior in this regard. So, as a summary, we can say that the oxDNA model is a top-down coarse grading approach, and the price you pay is really that you need to devise these bespoke interactions, which are quite complicated. You know? But there's no free lunch, as we probably all know. The potential consists of 1 bonded interaction and 6 pair interactions, and that allows you to get a very good, say, average. This is what we're working at now. Average confirmation of single and double-stranded DNA, both. Yeah. Many other models they're good for mostly double-stranded DNA. Maybe you're familiar with the Martini force fields. I don't know if it's a very popular coarse graining approach. They've got also they're very successful as well. I mean, I should say that before I continue. But their DNA model isn't really quite the same level of success because they can pretty much only describe double-stranded DNA and not the transition. This is what oxDNA gets extremely well, the thermodynamic properties of this. There is it's called Santa Lucia nearest neighbor model. I think it would lead too far to explain what that is, but it's what's behind all these servers that you can use to, for instance, calculate the melting temperature of a DNA sequence. LUPAC is one of them. Also, prediction of secondary structures. The model behind it is always the Santa Lucia. It's conceptually relatively simple, and oxDNA has been parameterized to on that Santa Lucia model to really get the denaturing transition right. So this is why it works really well in the thermodynamic domain. And then the structure is also reasonable, but we're trying to improve it further in a third version, but that will take some more time. This is kind of like what I indicate here. What we don't have at the moment, so we do have sequence-specific hydrogen bonding. So you know, or you don't, but now you know. AT base pairs have only 2 hydrogen bonds. CG have 3. This is why AT come apart more easily. Yeah. And this is, for instance, an aspect that is in oxDNA 2, sequence-specific hydrogen bonding. And then the stacking interaction has something similar, but it's on the level of the base step, what's called the base step, which is also where the Santa Lucia model works. A base step is, for example, CG on one strand. and the stacking interaction is not symmetric. So CG is different from GC. So you have 16 minus how many? 4? Is it 12? 10 different steps, 10 independent steps. I think it's right. Is it 10?
Oh, don't ask me.
It's like with the, it's like I always
I have to think about it.
Yeah, it's too early for that. Not even 10 o'clock. I think that's the
No,
time.
it's too early. Ollie.
It's too early. It's too early. Not enough coffee. So so this is also something that oxDNA 2 has, but what is currently completely missing is sequence-specific curvature. So DNA has an intrinsic curvature, and there are very famous examples. I always forget the name of this. This one is, I'll maybe dig it up and show you the picture during the break. You can get really something that is almost a 180-degree turn over like 200 base pairs of the strand, depending on the sequence. But if you have poly AT, yeah, AT, it is super straight, also over the same distance. So it's really a very important aspect that is currently missing. And you can see this is, when we think of like the first slide, or one of the first slides, these histone octamers, where it wraps around these proteins, you can see that intrinsic curvature is probably something that really matters. If there is already some kind of like intrinsic curvature over exactly that length scale of 200 base pairs, then it will probably be more easily found as one of the positions where one of those nucleosome core particles is positioned. Yeah. So that is something that we will endeavor to include here. And then there's also the sequence-specific elasticity. So how big is the resistance against bending of the strand? That is also an aspect that is currently neglected. Yeah. So here are two key references on the slides. This is all linked. I mean, if I'll just check what happens when I call this thing now. So you see it goes to the website, but the sharing is paused. I think because I'm not sharing the screen. I think I'm sharing only the application. So it is linked, and you go directly to the paper. So the first one is Tom's oxDNA 1, 2011. The second one is oxDNA 2, where they introduced the major and minor groove into the model, and then as well the electrostatic interaction. Yeah. So that concludes like the first part. And looking at the time, I mean, that was about like 40 minutes-ish. What we could do is just quickly look at, okay, what is the software? How do you get it? How do you compile in principle? Then have a break. Just to get,
ask everybody a question?
Oh yeah, of course.
I just want to see if you guys, so oxDNA, as Ollie will tell you, is implemented in LAMPS, which is a materials modeling piece of software. Can you guys guess from this talk why Ollie hasn't used Romax, Amber, or Nancy? Why do you think Ollie's had to use LAMPS? Yes.
Is it to do with force field parameterization?
It's very close. Yeah.
I'll take that.
Yeah, it's to do with the potential functions. So Ollie has these amazingly complicated potential functions, whereas Amber, Romax, and Nandi all have only these pairwise potentials. So the potential function in all of our normal atomistic codes is really simplistic, and you don't have the opportunity to add your own potential function. But LAMPS enables you to do that. So if ever you need a potential function that's not the normal one, then LAMPS is a good option. As D or poly is also an option.
Okay.
I'm not saying it's a good option, but it is an option.
there's a big infrastructure behind LAMPS, and well, we'll come to that in a moment. But what Sarah means is this: it's the bespoke. Here, this word bespoke. That's why. So you need to implement your own stuff.
Yeah.
It's about 14,000, I think, lines is 13,000 is the model in LAMPS.
So what Ollie's doing is he's saving computer time, but he's had to do a lot of work to be able to, because you know the functions are a lot more complicated when your model is simpler. If that makes sense. Sorry, Ollie.
No worries.
I don't mean to butt in. Sorry.
So good, then let's have a look at the software. So here's again an overview of what we really have. This is the whole oxDNA world, if you want. First is this LAMPS version developed by myself only, unfortunately. So it's I can tell you it's. It would be good to have a few more people doing the same. But what we have so far is oxDNA 1, oxDNA 2, of course. And I call it's normally called just oxRNA, but I call it oxRNA 2 because it has also major minor groove and it's in the very same way implemented as oxDNA 2, but it's the RNA model. What we don't have is like the cross thing, so DNA RNA. Because you would have to parameterize this. And we're hoping to develop maybe now a framework that allows us to do these things more easily. Yeah. So this is something for the future, but you can do DNA by itself and also RNA by itself. And this is provided through this CG-DNA, as it's called now, user package in LAMPS. I'll tell you more about this in a moment. Then there's the standalone version. This is a re-implementation of Tom's original PhD code, which wouldn't pass the test of scrutiny of research software engineering standards. I work with it, but so they re-implemented this, and it's definitely better, and it's the main distribution that people work with when they use this, when they don't use LAMPS. No? Then there is what's called TAC oxDNA. TAC is, or TAC is tools and converters for oxDNA. And then there is a really amazing tool, which is relatively new, is the newest kit on the blog, I think, is oxView, which is a visualization and data manipulation toolkit. So these images that you've seen before, they weren't done with oxView at the time, but oxView produces a very comparable design and or like layout, and so they look very similar. And the cool thing is as well that you can edit it, then export it as a new configuration. For instance, you can create bonds where there are none, things like that. So we're going to work in one way or another with all four of them during the hands-on part. And in the standalone code, there's also something which is called oat, like buckwheat or wheat or whatever, so OAT. Is Oxford analysis tools, yeah, oxDNA analysis tools. So these are this is integrated into the standalone code, and if we have enough time, I think it's not available on ARC, and I would be very impressed if you manage to install this now, because I think it's more like it has Python bindings, and if you don't know what to do on your weekend, that's maybe something. Yeah, so it took me about 5 or 6 hours to get it working. But these because I had to figure out what went wrong. Now I know. These are part of the standalone code, and they allow you to analyze trajectories. So I've got 2 examples of what you can do with them later on, and we'll probably show this more clearly. So the LAMS code is simply the acronym for like large-scale atomic molecular massively parallel simulator. It's got a really interesting story because it was initially released by Sandia National Labs in 1995. And Sandia is the US national lab that is traditionally responsible for the non-nuclear components of the nukes. Yeah. So the nuclear components, they were developed in Los Alamos, and the non-nuclear components, in other words, the explosives, they were developed by Sandia. So what they, I think this is my personal interpretation, but what they needed was a code that could do millions of atoms, classic force fields, to study shock waves, detonation, and this stuff. So it's got a very sinister start, I think, this whole thing. But then it went public, and there's so many people that use LAMS now, and I think this is the main use now. Yeah. Advantage is there's really an infrastructure behind it with these US national labs, which is really helpful. It's very popular. There's over 400,000 downloads over the last, well, it looks a bit long, but 17 years-ish. But I mean, how often do you download a code? I mean, I've done it a few times with LAMS, but I think probably not even 10 times in my life. Yeah. There's 1,400 forks on GitHub and about 100 direct contributors. So they develop different bits. It's got an amazing functionality, which is why it's very versatile. So you've got 91 standard and user packages. They used to distinguish between standard packages that are maintained by the core team and user packages that are maintained by people like myself, but they don't do this anymore. And you can run it on CPU, multi-core, GPU architectures, but not everything is supported on every architecture. For example, oxDNA is only CPU multi-core at the moment, and is also one of the projects in the pipeline to get a GPU port of this. Yeah. There's very useful stuff there as well in LAMS. There's this replica package which contains a collection of multi-replica methods like parallel tempering. Then there's Plumed, which is a free energy library for enhanced sampling tools. Yeah, very popular as well, used in many other codes. There's a Colvars module which allows you to define collective variables. You can also do this in Plumed. And these are just 3 examples of the stuff that you can find there, which is just there, and you can use it. You'd struggle to tweak your own code to use them. I think it's really amazing what is already there, and it became a lot more popular. This is what the developers told me. So they've seen still an increased uptake within the last 10 years. More and more people start using LAMS. The reason is it's very extendable. It's written in C++ with a very clear class structure, and they've designed it really well, I have to say. Yeah, I mean, otherwise it could be a lot more difficult, and they designed it to be extendable. To be the idea is it's not the top performance. If you compare it, for example, to GROMACS, GROMACS is always among the fastest codes. So it's slower than GROMACS, but GROMACS is like a black box. I mean, if your science is implemented, then you're fine. Otherwise, good luck to convince the developers to do it for you. Yeah. Whereas with LAMS, it's a little bit slower, but with some development skills that are probably not extreme, as in my case, for example, then you can develop your own stuff. Yeah, because the really complicated part is hidden from you. Yeah, yeah, it's great. It's great. So this is the LAMS code, and what you need is a C++ compiler, C++11 standard, and then you get it from I think this is mentioned here, available from the LAMS organization page. So if I click on this, I should go. Yeah, this is what the website looks like. So this is the main website, and then you go here on to download, and you go to the GitHub site. So you then change it into the source directory, and then you for oxDNA you load these 3 modules. It's one is called asphere, so we have rigid bodies. Then molecule, because we have the single-stranded DNA chains, and then cgDNA, and that's done with just say this is the traditional make way here, which make comes with your Unix system, so it should just work out of the box. So you load these modules, and then you just check with make ps that you have them loaded. I omitted those, and you get a bigger output normally when you do this, but I just omitted those that where it needs to say yes, and all the others it should say no. And then you say make serial or make MPI, so they are like vanilla make files in the distribution, and I don't remember a single time that they didn't work for me. They're probably not optimized, but they do work. And then there are more configurations in this directory that I mentioned here. For instance, if you have like an Intel machine or whatever, yeah. Yeah. Oh, sorry, there's an echo. It's myself. It's not a question. There's a in the chat something. I see something.
Yeah, that's what I was checking.
Okay, yes.
Someone working with RNA.
Yes. Yeah. Yeah. Any of those will be useful. Yeah. So you can use LAMS or you can use oxDNA standalone. So they both have this oxRNA forcefully implemented. Yeah. And the idea is ACGT. So it's type 1, 2, 3, 4 internally. And then for RNA, this type 4 changes to uracil then. Yeah, this is so you have also type 1, 2, 3, 4. Yeah, but again, as I said, like you can't do like the cross DNA RNA. Yeah, at the moment. Here's our implementation paper, which is partly outdated now. Which is why I point always to this thing here, which is part of this distribution. So I try to keep this reasonably up to date. So you see that it was like last year that I did some changes here, which gives you some details of how you configure data files, input files with the parameters. So that is meant to be a kind of more in-depth documentation that is reasonably up to date. So this is the LAMS code. The standalone version includes the same DNA models, oxDNA 1 and 2, and oxRNA. It's available from Lorenzo Robigatti's GitHub page, which is here. This is the oxDNA distribution. Here's Lorenzo. He's based at La Sapienza in Rome, and is one of the 3 main developers of the standalone stuff. You see, like I say, half a dozen of contributors, not in the hundreds, but with LAMS, I mean, with oxDNA, the only contributor actually is myself. Yeah. So so they've got about 3-4 people, 11 forks on GitHub. So it's a completely different order of magnitude, obviously. But one of the real highlights is, and this is what we decided during this first oxDNA workshop that we had a few years ago, is the Monte Carlo capabilities of the standalone code. the key problem with this kind of model is through the force field, the entities are what you could call strongly interacting. Yeah. So when you have a standard MC metropolis algorithm or whatever, what you would do is, well, you move one nucleotide a little bit, but because it's strongly interacting, energetically, your energy of that sort of like trial move shoots up already quite a lot because it's strongly interacting with everything else. Which means there's a very large probability that this gets rejected. So with a standard metropolis algorithm, you get just too many rejections in a force field like this. So you need to come up with something different, and this is called virtual move Monte Carlo. And the idea is that you move whole clusters. And through moving whole clusters, you have more movement. And when a cluster moves, then this kind of energy shoot up is not in the same way. So you get more acceptance compared to the standard metropolis algorithm. And this is what's really a key feature of the standalone code that you don't have in LAMS. We see these two implementations more complementary than competitors. So LAMS has currently doesn't work on the GPU. We'll get this at some point, but it's the main MD code, whereas the standalone version is the main MC code. Yeah. At the moment, it is supported on single core CPUs and single GPUs, and I think it will never be anything else than that. Yeah. With LAMS, you are now multi-core, but not GPU, not single GPU. But once we re-implemented it for the last time, then I think you can run on hundreds of GPUs. So what the guy told me, Stan Moore is the name of the developer. He said he ran like simple pair interaction benchmarks on thousands of GPUs, yeah, and it scaled well. So that would enable then you to do vast simulations with the LAMS implementation. The standalone code, I think, is too complex to organize anything like that for standalone code. I'm rather pessimistic, but it's single core CPU. We're going to use it single core CPU in the exercises, and then on single GPU. And then there is are these analysis tools available. They're quite handy. We'll also have a go on with them. Here's what you need to do. You need a C++ 14 standard compiler, a make version later than or including 3.5. Optionally, the CUDA toolkit version 10 or later. And then you change into this oxDNA top-level directory, create a build directory, and then use CMake to create your make files and then compile it. That normally works as well. I haven't tried the CUDA, but provided you've got these compilers and CMake, it also should work out of the box. If you want these oxDNA analysis tools, then yeah, bring some time. In principle, it should be only this, but there's a whole section which is linked here on known issues. Quite often what you need to do is you need to specify explicitly where the Python is, because of the Python bindings. So if you have diverse Python installations or libraries on your system, it won't find the right one by default. You need Python 3.9 or later, so anything older won't do it. But then it's also just doing make and make install. And what I found out is a full Anaconda 3 distribution is very is probably necessary. Yeah. So I did it with a mini Conda at first because I thought like I don't use this normally. Didn't cut it. Yeah. So yeah, another hour of my life passed without progress. But it's like you can get it working. It needs a little bit of determination. So yeah, there's more information on how to do that here on this documentation page here. This is all linked. Like this is the main oxDNA software documentation. It's quite nice, and I think it's very reasonable and very understandable. I think they've done a really good job here. So I think this is probably almost everything. There's just two tiny bits. These tools and converters, that is available as a web server, which has almost the complete functionality. I'll just go there as well quickly. So this is what it looks like. CISA is the in Italy, in Trieste, very beautiful, really great place. And so you can kind of like convert between different formats. I'll tell you more in a moment. And the alternative is also by just cloning from Lorenzo, of course, and then using it as a standalone. You just need some Python, and then the Python scripts, you run these Python scripts. So we're going to do maybe both. So this is this paper that came with it from Antonio. If you want to know more, and in general, like you kind of like click through here, and for instance, what's really handy is thing of like you've got a parameterized curve in 3D like this trefoil knot, but what you want then is, well, you want to actually have a DNA strand in that shape to study topological conditions, knots, and whatever. And TAC oxDNA can set this up, and then you can convert. Well, you set this up, and then you use this as an input for your MD simulation. And I think this is actually a mistake, because it should tell you here, well, this is a linking number 44, and this is 42, and then they run the MD simulation, and but these are identical. I think this must be a mistake, and the paper is taken from the paper, so the editorial team didn't notice. So
I didn't review it.
You?
I didn't review it.
Well, I know who did.
Ah.
Myself. But I noticed only now. It's like, but the thing is, the editorial team, I just blatantly blamed the team now, so I need to blame myself as well. But I just didn't see it. But now that I took the screenshot and put it in here, I immediately noticed. So yeah, you see how it goes. Yeah, so it's a really great tool, very helpful. Here is a short overview of what you can do. You can go back and forth between LUMS format and the native oxDNA format, PDB and native oxDNA format. So you see it's geared towards the native format, but you can use this as well as an intermediate. And then there's a few things that you maybe need to tweak when you do this, but it's not very complicated. And then what we've just seen with this trefoil knot is that would be a conversion between XYZ and the native form. This is like one direction, obviously. And then there are these DNA nanotechnology formats like Nano and CanDo, and I think Tiamat is another one. So there's a whole range of those. These are the most important ones, I think, for DNA origami. I think here this Nano is for DNA origami. So you know when you define, well, that is the structure, and here I've got like the stuff that needs to hybridize. So it's Nano is the design tool for this, and then it converts this into a native oxDNA format, and you can run it. So it's really very helpful. And the second thing then is this oxView thing, which is very helpful. So it is web browser based, which is why we don't need to install anything today. And they claim they loaded 1 million nucleotides so into a browser. It's not a mean feat, really. You can produce videos from the trajectories and yeah, edit as well your configuration, export it then. So this is available in various ways. There's Peter Schultz, who's at Arizona State University. On his GitHub page, if you just click this, it will load it directly into your browser. So I'm just going to do that, and you see it opens already. Oh, no, sorry, that was the wrong link, I think. But the second option is if you go down here and then you try it, then it does it. Yeah. So here's the interface. We're going to work with this in a moment. This is the page that I had in mind. So this is the direct link. It just opens it. And then, of course, you can do it that way, or you can run it locally by starting the Python server as well. But it's normally not necessary. Again, here like 8 and 9 are these publications. So they got a Nature Protocols recently, which I think is very well deserved because it's a really nice tool. They also do DNA protein interactions now with it. It's really cool. I think